In this video, we will talk about the maximum power transfer theorem. So this theorem is about how we can maximize the power that is supplied by a source to a load. And we'll specifically look at a calculus-based proof of a resistive circuit in order to go through this theorem. So on the schematic that is shown on the slide, we have a source that is put up in a red box right here. It has a constant voltage source Vs and a series resistance Rs. So that's our source. And for the load, we have connected one load resistor RL. So what we are going to try to do is we are going to try to see what is the power delivered to the load resistor first, and then later we can maximize this power. So for the sake of computing this power, I'm going to assume that I have a current I sub S that is coming out of this voltage source, and this current is going to be the same for both RS and RL because they are both in series. Now I can easily find this current out by using Ohm's law. I can write Is as Vs divided by the sum of the two resistors Rs plus RL. That's going to be the current that is supplied by the source to the load. Now, using this and the power equation, P sub L, that's my power that is absorbed by the load resistor, is VL times IL, where VL is the voltage across the load resistor and IL is the current through the load resistor. And in this case, as you can see, Is is going to be equal to Is. And VL, I'm going to rewrite this in a different form, which is IL squared times RL. Because again, if I use Ohm's law, I can write the power equation in that form. Now I know Is is equal to IL, so I can rewrite this as Is squared times IL. And Is I have computed earlier, so this power I can write as Vs divided by Rs over RL squared times RL. And if I rearrange a few things over here, I can rewrite this power as Vs squared divided by Rs squared divided by RL plus RL plus 2 times Rs. So this is going to be the power that is delivered to the load resistor, and as you can see in the numerator I have Vs squared, and if I use a constant voltage source over here, that is going to remain as is, and then the denominator depends on both Rs and RL. So clearly the power that is delivered to the load is a function of Rs, RL, and the source voltage Vs. Now if I consider that my source doesn't change, meaning Vs and Rs are going to remain the same, what value of RL will maximize this power? That's the objective. So what I'm going to do is I'm going to, on the next slide, try to maximize this power, and just so that I have this result over there, I'm going to copy it from here. So on this slide, we'll try to maximize this power equation PL that we derived on the previous slide. Now, maximizing P sub L can be also viewed as minimizing the denominator in that equation, which is RS squared divided by RL plus 2 times Rs, because I have a constant voltage source Vs. So maximizing PL should be the same as minimizing that function in which I have Rs and RL. And if I were to minimize this function, let me just call that, say, dr for denominator. So if I was minimizing this denominator and I'm trying to find the value of RL that minimizes this, I would have to compute its first derivative with respect to RL and set it to 0. So I'm essentially trying to find dr for denominator with respect to RL, and I'm going to set this to 0. And the value of RL that makes that happen is the value that I'm after. So if I go through this derivative here, I'm going to get, I'm trying to differentiate this function here with respect to RL. So the first term I'm going to get is negative RS squared divided by RL squared, and then I have a plus 1 from the second term, and then 2RS goes to 0 because it does not have an RL. And that needs to be set to 0, which implies that RL squared equals RS squared, which also implies that RL equals plus or minus RS. And resistors are positive quantities, so the only result that I need to worry about is RL equals RS, and that would be the condition for the load resistor for maximum power being delivered to the load. So essentially what this means is make this resistor equal to this resistor, which is also called impedance matching. Make them both equal, and that is what makes the maximum power transferred from the source to the load. Alright, so if I go back, my objective was to maximize this power. Let's just find out what that maximum value is. So P sub L comma max, the maximum power delivered to the load is, and I go back to that equation here, I get Vs squared, I have divided by Rs squared divided by RL plus 2Rs. And if I make RL equal to Rs, I'm going to get this to be Vs divided by 2 whole squared. So essentially that means that it's going to be half of the voltage and squared of that. Let me see, this is going to change a little bit here, I think. I get a Vs squared, and in the denominator I get 4. Sorry, I need to do this again. So I get Vs squared divided by Rs squared, 1 Rs gets cancelled, plus Rs plus 2Rs. So I've got Vs divided by 2 squared and 1 over Rs. So that's going to be my maximum power that is delivered to the load. And the important condition that we have seen over here is the load resistor equals the source resistor, and that's when this maximization of power happens. Now we can also look at a very simple Matlab analysis to validate this calculus-based proof. What I have over here on the left is a Matlab script, and I will walk you through this very quickly. The first thing I have done here in the first box is I have initialized circuit parameters. So what I'm considering a circuit in which I have a 9 volt constant voltage source, which is connected to a 35 ohm resistor, and which is later connected to a variable resistor RL. So this is my 35 ohm resistor here, and this is my variable resistor RL, and this is ground. So that's the circuit that I'm simulating in Matlab. The circuit parameters of that have been initialized. And in the next section, I'm trying to determine the current through each of the resistor. And as I said, they are going to be the same because the resistors are in series. And just as we did earlier in Matlab, I can say I, the current that is coming out of this voltage source, equals Vs, which is 9, divided by the sum of those two resistors. In this case, it's going to be 36 all the way to 135. So it's going to be a vector of values. And notice over here, I've used a dot operator to indicate that I'm trying to do this element by element. So Vs divided by a vector of elements in this case. So I'm going to do this element-wise division. Now in the next section, I have the determine power absorbed by the load resistor. That is simply the power equation, V times I, which is the same as I squared times R, or V squared divided by R. I have I from earlier, which I can square that, and then RL has been initialized to that vector, so I can multiply that accordingly. Notice over here, again, I'm doing element-wise squaring and element-wise multiplication here. Now, once I have the power absorbed by the load resistor, and I also have the load resistor values over which I'm doing this calculation, I can sketch on the x-axis RL and on the y-axis PL. So I'm sketching the power absorbed by the load resistor as a function. On the x-axis, I have the load resistor itself. That gives me a graph like this. So we can see that when the load resistance that's on the x-axis in ohms is between 1 ohm and 35 ohms, you have less power being absorbed by the load resistor. It increases as you increase the load resistance, and it becomes maximum when RL actually equals 35 ohms. And the y-axis is in watts. Right now we are not interested so much in the value of the power absorbed. We are just looking at what value of RL maximizes this, and it looks like it is going to be 35 ohms, and it makes sense, and it agrees with our proof from earlier, because RS was set to 35. So when RL equal to 35, that's when this maximum power was delivered to the load. And as you increase RL further beyond 35 ohms, it's going to come down. So that's the only time it gets to the maximum power. All right, so I hope this video was helpful. See you in the next one.